So now we're going to continue on with linked lists and what it would look like if we wanted to store our integers in this data structure. So let's say this is memory address 0, and then this is memory address, let's just say this is 40, and then this is 80. So now we have 3 different segments of memory. And so this segment starts at memory address 0 and goes all the way up to memory address 20. And this segment starts at memory address 40 and goes all the way up to memory address 60. And this segment starts at memory address 80 and goes all the way up to memory address 100. So in a linked list is comprised of elements called nodes. So in a node, there are 2 parts. So the first part is the value. So for instance, if we were storing the integer 1, our value would be 1. And then the second part is called the next pointer. So this is going to tell us what's the address of our next element. So the next pointer would store the memory address of our 5 if we were currently on the first node. So let's say our first element is stored at memory address 0, and we want to store our second element at memory address 40. So our second value of 5 is going to go here. This means the next pointer of our first element is going to tell us to look at memory address 40. So I'm putting the @ symbol here to indicate this isn't just an ordinary integer, but rather it's a memory address. So now let's say our third element is stored here at memory address 52. This is 52. So that means the next pointer for our second element is going to tell us to look at address 52. And let's say our 9 is now going to be stored at memory address 80. So then this will tell us to look at memory address 80. And then now, let's say we're only starting off with these 4 elements. This means that there is no next element, so we would just say our last element's next pointer is just going to be null. Now, similarly in this example, we inserted a 2, and remember we're trying to keep our list in increasing order. Currently our linked list has 1 pointing to 5, pointing to 7, pointing to 9. So we're trying to figure out how can we insert a 2 into this linked list so that the linked list actually looks like 1 to 2 to 5 to 7 to 9. So first we're going to have to find enough space for a new node. So we're going to need 8 bytes of free space. So right here seems like a good spot. This means that the 2 is going to point to the memory address of our third element, which is going to be memory address 40. And now we need to make the edit to make sure 1 is actually pointing to 2. So this means now our first element is actually pointing to memory address 12. So that's all we need to do to maintain our order. While remember for the array, we actually have to allocate a new segment of memory and copy over all of the elements. So this is our first pro of our linked list, is that we're going to have faster writes. And more specifically, it's going to be constant. Inserting an element is always going to take the same amount of time, whereas inserting an element into our array is going to be, in the worst case, linear. Now if we want to add an element to the end, it's going to be a similar process of finding some free space. And since we know this is going to be the end, this is now going to be pointing at null. Now we need to go to the preceding element and change its next pointer. So now our 9 is going to have a next pointer that's pointing to memory address 92. And now another pro is going to be it's more memory efficient. And what I mean by that is each node is actually going to take up more space. So each node is going to be 8 bytes compared to the 4 bytes we're storing in our array. But now we don't need our entire data structure to be contiguous. So if I wanted to store these 5 integers, I would need 20 bytes in a row to allocate that space. So for our linked list, we just need to find free space that is of size 8 bytes to store a single node. So now going on to the cons, we're going to have slower reads. So this goes back to the idea of the cache. So now if we're trying to load in a block to the cache, it's going to be a lot less likely that we're going to have multiple elements. So if we wanted to print out every element of our linked list, then our state of our cache at any given time might only have, let's say in this case, 1 node. So this means that we have to go back to main memory for each element that we're looking for in our linked list. So to wrap up here, what we did here was compare 2 different basic data structures in C, the array and the linked list. And so each has its pros and cons. So one isn't strictly better than the other, but it's context dependent. There are trade-offs depending on which data structure you choose to use. And there are other data structures that are meant to mitigate these trade-offs. So one example is something called a linked list with fat nodes. So what a fat node is, each node acts as an array. So each node is actually more cache friendly. So you can imagine, instead of our node consisting of 1 value and a next pointer, maybe instead we store value 1 and value 2. So maybe our node instead will look like this. So 1 and 2 are stored, and then we actually store a pointer to the next fat node. So this is going to be memory address 40. And then we can change this to the 7, and then store the address of our next fat node, which is going to be at memory address 80. And then here we can store our 9 and 10 right next to each other with the pointer to the next fat node. In this case, there is no next fat node, so the pointer is just going to be null. So the idea here is that we're trying to take the cache benefits of our arrays and apply them to our linked list. So this is kind of a hybrid between arrays and linked lists. So that wraps it up for today. Thank you for listening, and if you have any questions or feedback, please feel free to leave that in the comments. Thank you.